James McInnes, and
I'm Kyle Mackwood.
And this is our update video to prove that we are actually getting stuff accomplished.
Yay!
Yay!
Hooray!
Yay!
Yay!
And there's Matt on the camera. Today we're using a much higher quality camera built into his iPhone instead of a $900 camera. So,
All right.
Technology these days.
technology these days. But
All right.
we're reporting here from Val Avionics, the new lab here, so that we can do some work on our NAV 2000 project. This is Group 30 signing in. And today we're going to be working with this wonderful piece of technology. This is a network analyzer. What it allows us to do is it gives us our frequency domain response of a filter without actually having to have any power applied to it. And it operates between 300 kilohertz and 3 gigahertz. So it'll give us a rather good signal of how the flow of the signal is going through and how much attenuation we're getting. Here is our pride and joy that has been assembled, and the boards have been tested by the board house. This is the NAV 2000 main board right here. This is the NAV 2000 receiver board, and this is a completed NAV 2000 display assembly.
Okay.
So today what we're going to be testing, at least our goal in testing, is to test the RF divider, which is this small little filter section here, as well as testing the overall operation of the NAV board. We have some limited code installed in the microcontroller, so that way we can start up at a set frequency and have the two demodulators do their job, as well as the mixers, which are going to give us our IF frequencies and allow us to hopefully receive signals today.
All right.
So what we have here is we're looking at the input filter of the system. We're currently looking at the VOR output of the system, so that way we can see what's going on and how much attenuation we're getting. As you're looking at this graph here, this scale right here is in decibels, this scale right here is frequency in megahertz. We're starting at 75 megahertz and ending at 400 megahertz, so we can see the entire input bandwidth. The yellow line is the reflected signal, the blue line is the through signal. As you can see, at point 1, we're seeing 14 dB of gain. The reason why we're seeing gain here is on the board, we have a 20 dB low noise amplifier where we're pulling off the signal. So we're seeing the notch filter and frequency split, as well as the first stage of the VOR filter and the first gain stage. The fact that with a 20 dB amplifier we're only seeing 6 dB of loss is well within our requested spec for the 108 megahertz, which is actually significantly better than our simulation. Our marker 2 location is at 118 megahertz, and we can see that we're seeing 17 dB of gain, which is only showing a 3 dB loss. So overall, that is well within our specification and is going to provide us with great performance for the VOR. Let's see here. So, alright, we've zoomed in on our frequencies of interest, so that way we can see how much slope that we're looking at on the roll-off in the FM frequencies. As you can see, it rolls off quite quickly. We're still looking at 108 megahertz with point 1 and 118 megahertz with point 2. 108 megahertz, as you can see, it's still right at 14 dB, so 6 dB of loss. And channel 2, we're still showing nearly 18 dB, so using this closer spectrum, we can see that we're just 2 dB shy of having a 0 dB attenuation, which is amazing considering that we are using a tuned splitter. Generally, the best that you can see with just a quick and dirty splitter is 3 dB of loss. More likely 6 dB, but this is what we have and this is working, which is great news. Now, if we take a moment here and use the marker and walk down and look at some other points of interest, we can see here at one of our general radio frequencies of 106, we can see that we're at 12 dB, so we're seeing a good sized roll off here. And we continue going down at 105 megahertz. We're at 10 dB, so we've got 10 dB of loss. 104 megahertz, 7 dB, so we're looking at 13 dB of loss. 103, 6 dB, and 100, we're at negative 4 dB. So we're looking at over 25 dB of attenuation of radio frequency signals, which is rather good sized, especially according to FAA specifications through the TSO manual. And at the minimum, which is 88 megahertz, we can see that we're well below any detection point. That right there shows us that we are deep in the grass for the system, and being in the grass means that realistically we'd have to do some heavy digging to get a signal out of that. Cool. Alrighty, now we've hooked up and we're looking at the glide slope frequencies from 329 megahertz to 335 megahertz. You can see that we are hooked from the input port here, following this circuit path, through this amplifier here, to this easy to break point in the circuit. Looking at the network analyzer, we can see there's point 1, which is the start of our frequency of 329 megahertz, and point 2 is the end of our frequency at 335. Realistically, it's pretty flat for an RF filter. You can see that we're letting in quite a bit of extra space over here, but really that doesn't matter much because in our filtering we are more concerned with attenuating the localizer frequencies that are coming in at 108 to 112 megahertz. So as long as we are seeing a significant amount of attenuation, mind you this is starting at 300 megahertz, we're not going to have a problem with having a cross signal or additional intermodulation problems that will cause false readings. So as you can see, looking at point 1, we are seeing 8 dB of gain on this system, which considering that there is a 10 dB amplifier in here, we're only seeing 2 dB of loss. At point 2, we're looking at 7 dB of gain, which, as I said, for a 10 dB amplifier, we're still seeing 3 dB of loss, which is within our specification. Unfortunately, due to the way the board was set up, we can't look at just the input filter. So we have to use math to figure out how well this is operating. And as I said, we're seeing attenuations that are well within our specified parameters. Overall, looks like this is going to meet our necessary operational standards to receive the signals that we want to receive.
Okay.
This is looking at the localizer right here. What we're looking at right here is the localizer. We're seeing the input signal in the yellow and the outputted signal is in the blue. As you can see, the two signals line up pretty damn well. So we're seeing the signal come all the way in from the generator right here. This is our generator operating at 110.5 megahertz, and we're putting in a signal at 50 dBm. So realistically, we're looking at a relatively small signal coming in. It's going through our cable down into the receiver, going through the receiver, following the microstrip path into the demodulator. The demodulator and AGC are operating within expectations and coming out at that pin on the unit. Now I'm going to reduce the amount of power coming in down to 90 dBm. Now we're looking at 90 dBm. And we can see on the scope that there is a bit of noise riding on the signal now, but it is still very much recognizable as being a localizer signal. So we're seeing it come in, everything's looking good, and the AGC is operating properly because you can see that the signal size has not changed. So that is the localizer. Now we're going to look at the glide slope system, which we're going to be operating at 110.55, which corresponds to 329 megahertz. In the glide slope settings, we've changed our pin to look at the output there, and you're going to stop recording.
Okay.
Now we're operating in the glide slope. You can see up here that we have our glide slope signal coming in and the glide slope signal from the receiver board. It does have a bit more noise because we're missing about 40 dB of gain and an attenuator stage out of the receiver due to the fact that we don't really need that much gain. We only have to receive down to minus 79 dBm for the FAA specifications. So the input signal that we have right now is 50 dBm, and as you can see, it looks pretty darn good. No real distortion on the signal, operating within expected parameters. We take it down to minus 85 dBm. There is quite a bit more noise, but there is filtering that's installed in the main board, so we should be able to filter all that excess noise out and have a good looking signal.
Okay.
Alrighty, this is our receiver receiving a standard VOR signal from our generator here, going in through the antenna cable, following along this microcircuit path here into the demodulator and being demodulated in the system. We're receiving it at minus 55 dBm, and the signal that's being generated is up top here. The signal that's being received is down below. The reason why we're using a different oscilloscope instead of the Tektronix oscilloscope is because we actually want to see the aliasing of the signal. So we had to downgrade our oscilloscope to be able to see the aliasing. The aliasing is realistically showing the difference in the 9960 signal as it's going over the frequency range. These nodes right here are showing the lower speed part of the signal as it's going between 9930 and 9990 hertz. Down below here we have our outputted signal. You can see it's a little bit smaller here, but that's realistically because of the gain that we have in this system. And overall it is operating appropriately. Now it's just a question of taking it and putting it into our main board here and verifying its operation through the main board system. Once we have that checked out and approved, that'll be our complete system. But this is our receiver board, and it is, from what I can see in specifications, working on the attenuation. VOR subsystem needs to be able to operate down to 101 dBm, and, well, what we see on the scope looks like a giant mess. Realistically, it's more of a question of if we can dig this signal back out of the grass and put it back together and make it something legible. So we'll see what happens. I do know that if we take and put a standard audio signal in here, oh, that's right. I'm going to do this. Put a standard audio signal, it starts looking a little bit better, but not much. So it'll be fun. Okay. We'll see what we can pull out.